Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about true stress and true strain. So why this topic is important and why we need to study this. See, generally what we study is engineering stress and engineering strain. Those engineering stress and engineering strains are applicable only in the case of designing civil engineering materials. But actual stress developed in your body, actual strain developed in your body is something else. So that should be considered in the case of manufacturing fields. When you want to manufacture a sheet, then you will go into plastic deformations. Then you need to compulsorily consider true stress, because in that case, true stress and engineering stress have large difference. So that will make big impact in your design. So for this thing, we need to study about true stress and true strain. Then only we can able to understand where we can use engineering stress and engineering strain, where we should use true stress and true strain. So let us first discuss about engineering stress and engineering strain that we already completed. See, engineering stress is given by stress sigma engineering is given by P by A naught. A naught is original cross sectional area. Okay. Means whatever initial cross sectional area is there, that is we take in this formula. Right. Similarly, engineering strain in case of tension or compression is epsilon engineering is equals to change in length divided by original length L naught. Okay, this is original length. So this is about engineering stress and engineering strain. Now let us move to engineering stress. So let us move to true stress. True stress is given by sigma true will be is equals to P by AI. AI is instantaneous cross section. See, let us take 2000 newtons and A is equals to 200 mm square cross sectional area, and because of the loading the cross sectional area is reduced to 199.5 mm square. Then calculate engineering stress and true stress. Engineering stress will be 2000 newton divided by 200 mm square, right? Sigma engineering. But true stress will be sigma true will be 2000 divided by 199.5, right? So the percentage of error in this case will be very less, because the reduction in area is very less, right? So the instantaneous area, if you take instantaneous area, we will get exact stress, but the instantaneous stress which is changing from the original cross section area, that is very small. The changes is very small. So the whatever engineering stress and true stress are almost equal. So that will happen in the case of elastic region. In linear elastic region, we already know that the strains and stresses are very small, right? So the change in cross-sectional area, see, because of the strain only, there will be change in the cross-sectional area, right? But the strain in elastic region is very small, that we know. So the changes in area will also very small similarly. So engineering stress and true stress are almost equal. So we need to design a material. So we generally take, so whatever civil engineering elements we design, that we design for elastic region, right? So in elastic region, true stress and engineering stress are almost equal. Then why we need to bother about true stress, right? Which is somewhat complex. So that is the reason in elastic region, change in length is very small. So change in area will be small. So true stress and engineering stress are almost same. So because of this, in engineering applications, we use two engineering stress and engineering strain. But when we come to manufacturing field, in that case they will go to large plastic deformations. In plastic deformations, the strains will be large, right? And they won't recover that. So the change in cross sectional area will be more than the instantaneous change in cross sectional area, and the original cross sectional area has large difference. So then we need to include the true picture, right? The true picture is true stress. So we need to take true stress into consideration in case of manufacturing fields, because while manufacturing a sheet or wire, we will generally make that deform very long, ताकि we can get small to small cross sectional area, right? So we go into plastic deformations. Okay. So in manufacturing field, we need to consider proof stress and proof strain. In engineering field, we can generally consider engineering stress and engineering strain. That is the reason why we call them as engineering stress and engineering strain, because we use them in engineering applications. Okay. In case of structural design. So that is about in plastic region. We already discussed these points now. So let us read it out once. In plastic deformation region, changing area will be more significant. So most of the engineering applications never allow stress more than elastic limit. So for engineering applications, we can use engineering stress. In manufacturing field, material is loaded till plastic deformation region. So we need to consider true stress only. Okay. This we completed. Now let us go to relationship. See, we generally used engineering stress, but we need to know what will be the true stress. So can we relate both these two things? Means if we related these two things, if we know the engineering stress, we can directly get the true stress, right? So we can relate these things easily in case of incompressible materials. Let us take incompressible materials. Incompressible materials means del V will be is equals to 0, right? Change in volume will be 0. So initial volume, final volume will be 0. So sigma through engineering stress will be is equals to P by A naught. Sigma true stress will be is equals to P divided by AI. Let us multiply by A naught and A naught, and let us take this. Okay. Then we will get sigma engineering into A naught divided by AI, right? So what is the initial volume of the rod? Initial volume will be A naught into L naught. The instantaneous volume will be AI into Li. Both these two should be same, right? So A naught divided by AI will be is equals to Li divided by L, right? So we can write sigma T will be is equals to sigma engineering Li divided by L, right? So what is Li? Li will be is equals to L plus some delta L, means del L we can say. So sigma T will be is equals to sigma engineering into L plus del L divided by L naught. So that will be is equals to sigma engineering into, sorry, this will be L naught, right? So 1 plus del L by L naught. So what is del L by L naught? Change in length divided by original length, that is engineering strain. So sigma T will be is equals to sigma engineering stress into 1 plus epsilon. Epsilon is engineering strain. So this is the relationship between engineering stress and proof stress in case of incompressible materials. So this is incompressible, sorry, this is engineering stress and this is engineering strain. So if we know engineering stress and engineering strain, we can directly calculate the true stress. So with this, we complete today's lecture. Next lecture, we are going to discuss about true strain. Thank you.